All right, so in this video, we are continuing our derivation of the C6H character table. And where we've gotten to this point is we were able to derive all of the irreducible representations. And we knew that we were done deriving the irreducible representations because we have 12 classes. And if we sum up the dimensionalities of these classes, 1 plus 1 plus 2 plus 2 plus 2 plus 2 plus 1 plus 1, we get 12. However, we know that one of the character table rules, the first character table rule, is that the sum of the square of the dimensionalities has to be equal to 12, the order of the point group. And if we do 1 squared plus 1 squared plus 2 squared plus 2 squared plus 2 squared plus 2 squared plus 1 squared plus 1 squared, that doesn't equal 12. Furthermore, the total number of irreducible representations in any character table has to be equal to the number of classes. And we only have 8 rows here, 8 irreducible representations, but we have 12 classes. So the way we're going to fix this problem and the origin of this problem is that the irreducible representations here aren't actually irreducible. They're what we might call pseudo irreducible representations. They're technically reducible, and they can be reduced into complex functions. Okay, and so our characters containing complex values. And so what we're going to end up doing is splitting each of these EUs, each of these E's into components that have 1 as dimensionality. So basically, these are going to get crossed out. They're going to get eliminated from our character table. And instead, what we're going to get is we're going to get these same Mulliken symbols, but each of these is going to be broken up into 2 irreducible representations with dimensionality 1, and we're expecting to have complex functions containing imaginary values that transform as these, and also having some imaginary values in here. So that's how we're going to fix this. That will give us a total of 12 ones. So we'll have the same number of irreducible representations as we have classes, and also 1 squared across the dimensionalities here. Well, it's just 1 squared, adding that up, 12 of them. So that's going to equal 12, which is equal to the order of the point group. So our character table rules are still going to be valid. And so what I've done on this slide is I've just combined things here. So put it in a more compact format. That's not my handwriting, so that we have some more space to operate with. But as a first step, what we're going to do, let's work through breaking up this E1U. And the reason why I chose that one to break up first, so I'm going to cross that one off. We're going to break up this E1U. And so it's going to break up into a 1 and a 1. And the reason why that's a good place to start is because it transforms together as the simplest function here. It's x and y. And so we're going to be looking for a function that basically the complex conjugates sum up to give x or sum up to give y. And that function, one of those functions is x plus iy. Okay, so if you take x plus iy and you add it to x minus iy, which is the complex conjugate, you're going to get x, and we know x transforms as E1U. So now what we can do is just ask the question, how does x plus iy transform with all the different symmetry operations in this point group? So it's just like what we always do, except now we have a complex function. So we apply the identity operation, the first operation in the first class, x plus iy. Of course, identity takes it to itself. So x plus iy goes to x plus iy. We would then have a 1-by-1 matrix, right, that describes this transformation, which is just value of 1, like what we always do. And then we would take the trace across that matrix and we get a value of 1. So we would get that chi of identity is equal to 1. And that's why we have a 1 here. We already have that one marked down. Let's do a C6. So with a C6, we have to recall our 2x2 rotation formula, which takes xy, takes not x times y, the matrix x and y, and takes it and rotates it by 60 degrees. So it's 2 pi over 6, pi over 3, negative sine 2 pi over 6, sine 2 pi over 6, cosine 2 pi over 6. And so what that tells us is that when we take x plus iy and we transform it with C6, x, the x component of this is actually going to go to cosine, I'm going to just write pi over 3, x, that's just simplifying 2 divided by 6, 1/3, minus sine pi over 3y. That took care of the x part, and then the iy part. Well, then we just show how y transforms with C6. So this bottom part of the matrix, timesing it by I. So we're going to get plus I sine pi over 3 x plus I cosine pi over 3y. Okay. And so at this point, we can actually factor out an x plus iy. And what this ends up being is, well, let's think about this. We can factor out a cosine pi over 3 and an I sine pi over 3. Sine. And just to prove to you that that's true, let's FOIL this back out. So x times cosine pi over 3 gives you this term. X times I sine pi over 3 gives you this term. Iy times cosine pi over 3, well, that's right here. And then we have Iy times I sine pi over 3. That's going to get us I squared sine pi over 3y. Well, I squared is equal to -1. So we get a negative sign there, and that's this term, because I is equal to root -1, right? And at this stage, we should recognize that this value here, okay, this complex number here, is actually in the form of the Euler's formula. And Euler's formula, remember, is this beautiful equation in math, which is e to the pi, e to some angle, e to theta I equals cosine theta plus I sine theta. And so e to the pi over 3 I is going to equal to cosine pi over 3 plus I sine pi over 3. And that's such an important quantity, that number in this character table, that we're actually going to define it as just a Greek letter to help us make a compact form of this character table. We're going to define it as epsilon. And so what we can write is that this is actually equal to epsilon. And so now we figured out that actually we have a 1-by-1 matrix that explains this transformation. C6 takes x plus iy and times it by epsilon. And so now we take the character of this matrix, right, the sum across the diagonals, what's only a 1-by-1 matrix, and we get that chi of the C6 transformation is just equal to epsilon. And so we can put that right here in our character table. So we can do a similar sort of process for the other operations. And so instead of for all these rotations having to actually go through them, what instead we can think about is, all right, for C3, what's going to change here? Well, this pi over 3 is now going to become, we're rotating by 2 pi over 3. And so all this is going to stay the same. And our character at the end is going to be equal to, I'm just going to write in black here, not e to the pi over 3I, but e to the 2 pi over 3I. And if we work through actually what that is, that equals cosine 2 pi over 3 plus I sine 2 pi over 3. Well, cosine 2 pi over 3, 2 pi over 3 is 120 degrees. And that's actually just equal to negative cosine pi over 3. Okay? So cosine of pi over 3, that's cosine of 60 degrees, that's 1/2, and this is cosine of 120 degrees, that's negative 1/2. And then sine 2 pi over 3, what is that equal to? That is equal to root 3 over 2, which is the same as sine pi over 3. So we get something that, with that part just stays the same, but we can put it in terms of pi over 3 now. And the reason why we're doing that is because now we can get it in terms of epsilon. And so actually what this is equal is to negative of the complex conjugate, which we use by epsilon, which an asterisk of epsilon, because the complex conjugate of epsilon is just taking the epsilon value and making the negative part, making the imaginary part negative. So we have a minus I sine pi over 3. Well, if we take the negative of this, then we get negative cosine pi over 3, and we get a positive I sine pi over 3. So this is just a compact form way of writing e to the 2 pi over 3 over I with this epsilon definition. And so we get negative of the complex conjugate of epsilon. And so, more generally, what we're getting here is that basically we have, cosine of theta plus I sine of theta. So we can keep going. And for C2, we're going to get that it's equal to e to the pi I. Okay. And that, of course, equals cosine pi plus I sine pi. Well, I sine pi 0, cosine pi is negative 1. So that's going to get us a negative 1 here. We could have also thought of that as, we know we're doing a 180-degree rotation. X is going to go to minus x, and y is going to go to minus y. So we're ending up going to get x plus y, x plus iy goes to negative x minus iy, which is just the negative of itself. So it makes sense that we got a negative 1 value here, but it works with these trigonometric formulas. Let's keep going. So our next one is C3 2 times. So the character of that, chi of that, is going to be e 4 pi over 3 times I. It's cosine 4 pi over 3 plus I sine 4 pi over 3. Well, cosine of 4 pi over 3 is doing a 200, is doing a 300-degree rotation, 300-degree rotation, right? Because this is basically 120 degrees more than 1 pi. So 120 plus 180 is 300. 300-degree rotation gets us to the bottom right of our unit circle. So this cosine is going to be 4 pi over 3. That's going to be equal to 1/2. Well, that's the same as when we had cosine pi over 3. But now we're at the bottom of our unit circle, so this is going to be minus root 3 over 2, which is minus of which is minus of sine pi over 3. Sorry, mental math here was done wrong. So 4 pi over 3 is 240 degrees. So we're bottom left of our unit circle. So that's going to mean cosine 4 pi over 3 is negative 1/2. So that's negative cosine pi over 3. So this is just equal to negative of epsilon, right? Negative of this. So that gets us a negative epsilon. And we just keep marching across in this way. Our next one is C6h. Character of that is going to be e to the 5 pi over 3i, which is equal to cosine 5 pi over 3 plus I sine 5 pi over 3. Cosine 5 pi over 3, now we're at 300 degrees. So that equals cosine pi over 3, but we still have a minus I sine pi over 3. And so that one now is going to get us, that's just the complex conjugate of epsilon, because just the imaginary component was negative. So we're marching right along. Our next one's inversion. Well, inversion, we know what that does. It takes x and y, z, any arbitrary point, and goes to minus x minus y minus z. So if x and y are both going to the negative of one another, our function, right, which is x plus iy, can't forget what we're doing here, goes to negative x minus iy, which is just equal to the negative of what we started with. So there we're going to get a negative 1. Okay, and then we can go to these improper rotation axes. It's actually easiest to first think about the sigma h, because the sigma h is embodied in these improper rotations. So let's skip to that one. And we know that the sigma h is in the xy plane. This is our principal rotation axis, our C6. And so if we have an x vector or a y vector that we're thinking about, and we have a horizontal mirror plane sigma h, we've done this many times, x goes to x and y goes to y. So this is just going to be like identity. So the character is going to be equal to 1. X plus iy is going to go to x plus iy. So let's put a 1 there. And now that we figured out that sigma h doesn't do anything, we do the same old trick that we always do. We have this S3 5 times. And so we know that an S3 5 times is just equal to a C3 5 times followed by sigma h 5 times. But we know a C3 5 times is equal to C3 2 times, right? And followed by sigma h. And so really, since the sigma h doesn't do anything for x and y, we're going to transform the same as the character for C32, which was as the character for C32, which is right here, which is negative epsilon. And very similar sort of logic for S6 5 times, that equals a C6 5 times, followed by sigma h 5 times, which is just equal to sigma h. Sigma h doesn't do anything. So we're going to be the same character as C6 5 times, which is the complex conjugate of epsilon. Okay. We already did sigma h, and now we do S6. And so S6 is equal to C6 followed by sigma h. Sigma h doesn't do anything for x and y here, so we just get the character for under C6, which is epsilon. And then lastly, we have an S3. S3 is just the same as C3 followed by sigma h. Sigma h doesn't do anything, so we're the same character as under C3, which is negative of the complex conjugate of epsilon. So that's how we derive this irreducible representation. We have to derive its sort of partner, its component. And the way that we do that is we know that, I'm just going to call this value a. We could go through the same logic with x minus iy, but there's an easier thing that we can do. We know that epsilon plus a has to equal this value that we crossed out. So, for example, 1 plus 1 had to equal 2. And here we know that a plus epsilon has to equal 1. So that's the value that we had. So a equals 1 minus epsilon. So now we just have to do 1 minus epsilon. Well, what's epsilon? Epsilon is cosine pi over 3. Cosine pi over 3 is 1/2. So 1 minus 1/2 minus the I sine pi over 3. Okay, well, that gets us positive 1/2. Well, what's positive 1/2? Positive 1/2 can also be written as negative. Positive 1/2 can also be written as cosine pi over 3. Back to where we were. So now we have cosine pi over 3 minus I sine pi over 3. Let's fix this. Well, that's just the complex conjugate of epsilon. So A we can replace by the complex conjugate of epsilon. And you can do a very similar thing for all of these. In this case, if we call this B, we're going to have B plus the negative of the complex conjugate of epsilon equals -1. So that means B equals -1 plus the complex conjugate of epsilon. Well, here's the complex conjugate of epsilon. So if we take -1 plus that, well, we know cosine of pi over 3 is 1/2. And so we're actually going to get -1/2 there. And we're going to get minus I sine pi over 3. Well, this we can just write -1/2 as negative of cosine pi over 3. And we still have the minus I sine pi over 3 part. And that's just equal to the negative of, that's just equal, what is that equal to? That is equal to negative of epsilon. So if you look at what epsilon is, it's right here, it's just a negative of those values. So that feeds in right here. So we've done all the hard computations at this point, or arithmetic. What plus -1 equals -2? That's -1. What plus negative epsilon equals -1? Well, we just did that. That was negative of the complex conjugate of epsilon. what plus complex conjugate of epsilon equals 1? We did that over here. That was epsilon. What plus -1 equals -2? That's -1. What plus -1? What plus negative epsilon equals -1? We did that over here. That's the negative of the complex conjugate of epsilon. What plus the complex conjugate of epsilon equals 1? That's epsilon. What plus 1 equals 2? That's 1. What plus epsilon equals 1? That's the complex conjugate of epsilon. And what plus negative complex conjugate of epsilon equals -1? That is negative epsilon. And so at this point, we have actually derived this x plus I, y vector. And so that's a good point to take a break before moving on and breaking up these components further.